Standard HTTP is a one-way street. A client sends a request, and a server returns a response. By design, the server cannot initiate contact or push unprompted data to the client. This diagram shows how we initially tried to solve this. On the left side, we have polling. The client rapidly asks the server for updates over and over, returning empty responses and wasting massive amounts of bandwidth. On the right side is the actual goal, a persistent bidirectional line where either side can talk at any time. To get that bidirectional line, we don't build a new protocol from scratch. We hijack HTTP. We use its standard ports and its routing infrastructure just long enough to establish a connection. Then we permanently break the request-response rules. True real-time communication requires abandoning the request-response cycle entirely. Here is exactly how we initiate that break. Looking at this sequence flow, the process begins with a standard HTTP GET request. The client asks to upgrade the connection and provides a random base64 encoded security key. The server takes that key, computes a specific SHA-1 hash, and returns it alongside a 101 switching protocol status code. The moment that 101 response is sent, the HTTP machinery is turned off. The TCP socket doesn't close. It is surgically detached from the web server and left exposed and naked. Because HTTP is completely gone after this point, this handshake is your only window to authenticate the user using standard middleware like cookies or bearer tokens. If you miss it, you have to build custom auth over raw TCP. Without HTTP's text headers, data is now transmitted in highly compact binary structures called frames. These frames flow in both directions simultaneously without waiting for a request. This layout shows what actually travels over the wire. The header is as small as 2 to 6 bytes. It contains a 1-bit FIN flag, a 4-bit opcode telling us if the payload is text or binary, and a payload length indicator. If a payload is too large, the protocol deliberately slices it into multiple smaller frames. It sends these pieces with a FIN bit set to 0, indicating more is coming, until the final piece arrives with a FIN bit of 1. For data moving from the client to the server, there's an extra step. The client must XOR mask its payload against a rotating 4-byte key. This scrambles the data to prevent cache poisoning attacks on transparent proxy servers sitting in the middle of the network. Engineers who don't understand this binary framing layer often see split messages in their logs and misattribute them to broken application logic, completely missing that fragmentation is an expected protocol behavior. Once the connection is established, it faces an immediate and visible threat in production, the network middleboxes, like NAT gateways and load balancers, sitting between your client and your server. Looking at this network map, if a TCP connection sits completely idle, a NAT gateway will increment an internal timer. If that timer reaches 30 to 350 seconds, the gateway will silently delete the routing table entry without sending a termination signal. Both the client and the server still think the connection is perfectly alive. OS-level TCP keep-alives rarely prevent this. Load balancers routinely ignore them, and the default Linux intervals of 2 hours are far too long for real-world idle timeouts. To survive, you must use application layer ping and pong control frames. Forcing this specific opcode across the wire triggers an immediate pong echo from the client, successfully resetting that Middlebox timer back to 0. Failing to instrument strict read deadlines for these pongs entails silent connection death. When those dead connections are finally discovered, thousands of clients will try to reconnect at once, potentially overwhelming your authentication services. Because both sides of a WebSocket can talk at exactly the same time, the backend server must allocate 2 independent concurrent loops for every single connected user. This concurrency schematic shows the canonical architecture in Go. A single TCP connection is branched into 2 isolated memory processes, a read pump and a write pump. This enforces a strict single-writer discipline, so the concurrent loops don't corrupt the data stream. If a network read fails and the application ignores the error instead of cleanly exiting the loop, the read pump stops. The message channel fills up, causing the write pump to freeze, leaving both processes permanently orphaned in memory. At scale, server crashes are rarely caused by the size of the data payloads. They crash because tens of thousands of these orphaned connection loops silently consume all available stack memory. Keeping individual connections alive is only the baseline. The real distributed systems challenge is fan-out. attempting to deliver a single real-time event to 100,000 uniquely pinned stateful client connections at the exact same moment. This visual shows a central hub routing messages. If you iterate through a registry and use blocking channel sends, a single client with a slow connection will fill its buffer. That one slow client freezes the entire broadcast loop for every other user. To scale this, the architecture has to change. You must use non-blocking channels that instantly drop slow clients. Then, you synchronize state across multiple isolated servers using an external pub/sub bus to duplicate the broadcast stream. This complexity forces an engineering trade-off. For one-way notification feeds, server-sent events often prove more efficient, offering lower memory overhead and native support for HTTP2 multiplexing. Operating a WebSocket service means taking responsibility for raw binary frames, manual keep-alives, and concurrent memory architecture, a level of ownership that goes far beyond standard HTTP.